Hello, discrete math fans. All right, let's create a sequence. The sequence starts d of 0 equals 2, d of 1 equals 5. And then, for future values of d, I'm going to give you a formula. So when n is bigger than or equal to 2, the formula goes d sub n is equal to 5 times d sub n minus 1 minus 6 times d sub n minus 2. Now in the next section we're going to talk a lot more about this type of sequence, but this is a recursively generated sequence. In order to get a particular term in the sequence, you have to do something with previous values. Now I'd like to prove that d sub n is equal to 2 to the n plus 3 to the n. That's a pretty remarkable statement, that you've got this pretty innocent looking formula that creates the value of the sequence, and it just turns out that there is a nice formula that tells you the values of the sequence. That's pretty cool. Let's let p of n be the predicate that d sub n is equal to 2 to the n plus 3 to the n. We're going to try to prove that that's true. Let's note that d sub 0 is equal to 2, and of course that's 2 to the 0 plus 3 to the 0, so p of 0 is true. And in a similar way, we can say that d sub 1 is 5, we're given that. That's 2 to the first plus 3 to the first, so p of 1 is true. So here's a situation where we're going to have two basis steps. All right, now for the inductive hypothesis, let's assume that p of k is true for k between 2 and n, and that's for n bigger than or equal to 2. We want to prove that p of n plus 1 is true. So that is, we want to prove that d sub n plus 1 is equal to 2 to the n plus 1 plus 3 to the n plus 1. All right, let's see if we can say something about d sub n plus 1. According to our recursive formula, that's equal to 5 times d sub n, that's the preceding term, minus 6 times d sub n minus 1, that's the terms 2 before. Now, here's the key idea. The key idea is that our inductive hypothesis tells us that we can rewrite d sub n as 2 to the n plus 3 to the n, and can rewrite d sub n minus 1 as 2 to the n minus 1 plus 3 to the n minus 1. Notice that we need a strong hypothesis here, because we're not just saying something about d sub n, we're saying something about a previous term as well. All right, we multiply everything out, do a little distributing, nothing fancy here. If we recollect everything, what we'll see is we'll get 4 times 2 to the n minus 1 plus 9 times 3 to the n minus 1. And, aha, 4 is 2 squared, 9 is 3 squared. So what do you know? We end up with 2 to the n plus 1 plus 3 to the n plus 1. That's what we wanted to prove. So, therefore, p of n plus 1 is true. And by the principle of strong mathematical induction, p of n is true for all n bigger than or equal to 2. Okay, that's all for now.